In this simulation, we're going to control the rise and fall of the ball. Notice that the initial velocity is now set at 20 meters per second. Let's click play. And let's use the graph to find how high the ball goes and how long it takes to get there. So the ball reached a maximum displacement of 20 meters within 2 seconds. Now let's click Reset to reset the screen, and we're going to use the initial velocity control to increase the speed at which the ball is thrown upwards. Let's increase it by 10 meters per second to reach 30 meters per second. So the initial velocity is set at 30 meters per second now. Let's click play. So how does the motion of the ball change? Exactly, it rises higher and it takes longer to reach its highest point. So it reaches about 45 meters displacement in 3 seconds. Now let's click Reset, and we're going to try 2 initial velocities, where one is twice the other. First, we have investigated the 20 meters per second, so now we will test the 40 meters per second. Let's click play, and observe the ball as it's going up and then going down. How does the height change when the velocity is doubled? Recall that for the 20 meters per second, the height was around 20, and it reached the highest displacement in 2 seconds. Now the displacement is 80 meters. So doubling the velocity increases the height by a factor 4, from 20 to 80 meters. Suggest the relationship between the initial velocity and height. Well, yes, you are right. The maximum height is proportional to the initial velocity square. Use the equation v squared equals u squared plus 2as to see where this relationship comes from. In this case, v is the velocity at the top of the path. If v equals 0, and a equals g, u squared equals to minus 2gs. Rearrange this equation to get s equals to minus u squared over 2g. If upwards is positive, g is negative, so s will be a positive number equals to u squared over 2g.